The information that I'm about to share with you I've never seen anywhere else. I'm sure there are other people out there aware of this information, but I've never seen it shared before. It comes from years of studying, experimenting with, and building permanent magnet motive force systems. There are three types of permanent magnetic motors. I'm not going to get into electromagnetics or kinetic energy devices. I'm simply referring to permanent magnet motive force systems. And the thing that might surprise a lot of people is that there is one man that was not only aware of these three systems, but is also the only person I'm aware of that holds patents in all three magnetic motor systems. That man is Howard Johnson. The three types of magnetic motor systems are imbalanced system, which is the most common, the induction expulsion system, and the exchange force pulse system. Each of these systems can be built in linear or rotary motor assemblies. I will cover all three of the types, what they are, how they work, how to test an assembly to see if it functions correctly in subsequent videos. In this video I will be focusing on imbalanced systems. The parent dev motor. Yilmur-Yildiz magnetic motor. James Roney shielded stator magnetic motor. The V-gate motor. And Howard Johnson's most famous magnetic motor, which was featured in Science and Mechanics. What do they all have in common? They are all imbalanced systems, or spin alignment systems. Now, what exactly is an imbalanced system, and how does it work? It is a magnetic assembly that imbalances the cogging effect created by the electron spins of the magnets in close proximity to each other, whether it be the fields between the track magnets and a cart, or stator array and rotor. This is done by careful creation of spin alignment patterns by use of correct spacing of shielding, distance and location between the assemblies of magnets. It may employ different types of magnets and types of shielding material in complex geometric assemblies. It often requires precise measurement and spacing and exact dimensional assembly of complex magnetic patterns. This is the whole theory behind designs like the parent dev motor, and the science of systems like Howard Johnson's most famous magnetic motor design. In order for a design like this to work, there has to be an arrangement of magnets that can be effectively looped together for continuous rotation. The best way to test an assembly is by first building a flat track version of the design. By starting with a linear assembly, you exclude certain complex variables that you will have to compensate for in a rotary assembly. When you build a rotary assembly, you have to compensate for flux loops that are created by arcing an arrangement of magnets into a circle, the magnetic variances of the backside of your rotor magnets affecting the opposite side of your stator, if they are on the interior wall of the motor, the effect that the metal from the shielding material has on your entire assembly, etc. So it's very important to understand what you're looking for in a linear assembly in order to ensure that you actually have a design that can be used to build an imbalanced system. Knowing is half the battle, and will save you hours of wasted time and money. If you pay close attention to what I'm about to share with you, you will fully understand how to spot a design that can be used to build a working magnetic motor based on this design type. You'll also easily be able to spot configurations that can't. You'll be able to easily distill through designs that other people post and know whether it's something useful to experiment with or simply a fun distraction. One of the core misunderstandings in building magnetic motor systems is that when somebody comes up with an idea that works well in a small assembly, they think it's possible to arc the geometry of it and make a rotary assembly. It's always wise to test your ideas in a linear track before taking the time to try building a complex rotary assembly. This assembly is based on a patent by George Sukup. Sukup based his design on the Robert Callaway V-gate, even though he takes credit and calls it the Sukup V-gate on his patent. This video clip is a test of his design using a linear track. You'll notice that they used 3 successions of V-gates and left the holes at the end of the assembly where they could have put a 4th. There's a very good reason for that. I'll explain in this miniaturized version using the exact same configuration. The importance of lengthening the track is to ensure that the configuration you're testing really works. For example, this V-gate assembly works well through the first 2 successions of V-gates, but it begins to slow in the 3rd, and it fails in the 4th. So there would be no point in building a rotary version of this configuration of the V-gate because it simply won't work. That's not to say that there's not a configuration of the V-gate that won't work, but this one will not. Most magnetic assemblies exhibit something I refer to as the spring effect. Now, magnets are not like springs. I hear that analogy all the time, and people who use it often don't have a really strong understanding of magnetic fields. Regardless, many tracks exhibit the spring effect. Once you push past the area of repulsion at the entrance of the track, a cart or rotor will shoot through the track and out the other end. Don't fall into the trap of being too excited about achieving this effect. Often, when you extend the track, you will notice that the spring effect reaches a certain point in the track where it's really just winding down. What your track must do in order to work in an arc geometry is to be able to start a cart at various points and still travel successfully out the other end. If it fails to do so, or is drawn right back into the track at the exit point, then there is no need to build a rotary version. It just won't work. If you build a long track and there's a dead zone right in the middle of the track, then it also won't work in a rotary assembly. A simple rule of thumb that I've discovered is, if you're combining or looping a particular configuration, whether it's a V-gate or one of Howard Johnson's styled configurations, put together at least 5 or 6 of these in a flat track. If you can pass through all 5 or 6 without the cart noticeably slowing down or stopping, then you may have something. Definitely build and test a rotary assembly. Consistent, consecutive motion is the goal. Without that, you have only a clever pile of magnets arranged in an interesting way that accomplishes very little more than to entertain. Because in a rotary version, the magnets are all lined up in a row. You won't have the advantage of starting at the opening of a succession of magnets and shooting out the other end, unless you build the assembly separately and generate enough motive force to jump from one magnetic assembly to the next without slowing. It's okay to have dead zones, which are areas that a cart or rotor will stop dead in a track or stator assembly, so long as you can move the cart or rotor into a motive force zone, which is an area of the track or stator where it begins to move and continues in a forward momentum through every dead zone without stopping or stalling. So in summary, a magnetic assembly that accelerates a cart through a track does not necessarily qualify as an imbalanced or spin alignment system. In a true imbalanced system, a cart or rotor can be stopped and restarted in various places along a magnetic assembly or stator, and it will still accelerate to the end of the track, or will consistently rotate in a rotary system. There can be areas of magnetic flux that create dead zones in the track so long as motive force zones of movement balance the system out and cause it to coast past the dead zones. The best imbalanced system will exhibit no dead zones though, even when you build an extended track. When you see an assembly that functions this way, even when you restart the rotor or cart at any point in the assembly and it still works, you know it's a true imbalanced system. Thanks for watching. Join me next time when I'll cover the second type of permanent magnet motive force system, the exchange force pulse system. Do great things. The information that I'm about to share with you I've never seen anywhere else. I'm sure there are other people out there aware of this information, but I've never seen it shared before. It comes from years of studying, experimenting with, and building permanent magnet motive force systems. In case you missed it, in part 1 of this series I covered the imbalanced system. I explained how it worked and how to test the assembly. I also pointed out that Howard Johnson is the only person I'm aware of that holds patents in all 3 systems. If you missed it, go check it out. The 3 types of magnetic motor systems are the imbalanced system, which is the most common, the induction expulsion system, and the exchange force pull system. Each of these systems can be built in linear or rotary motor assemblies. In this video, I will be focusing on the exchange force pulse system. It's glaringly obvious the first time you run a magnetic cart down a track past an arrangement of magnets that the force equals out, giving you zero gain. I call it the spring effect. Sometimes you can even get to within an inch of full rotation. This I call the 1-inch barrier. In a conservative field, the total line integral around a standard loop equals 0. A perfect system cannot produce any more out than you put in, meaning that configuring a wheel with magnets and running it past a magnetic stator assembly without employing some type of shielding, spin flipping, or methodology for imbalancing the magnetic flux between your rotor and stator assembly will not produce continuous rotation. The fields will always seek an area of low resistance and come to a stop. What you need to get beyond this is a non-equilibrium steady-state system. This is a system that uses the steady stream of electron flow from the magnets like a sail uses the wind for motion. However, the electron spins of a magnet are a bit more complicated. It is understood in spintronics that there is a small particle in a magnet that is opposite charged to the pole it is emanating from. This particle's effect can be perceived at right angles of the moving electron. Howard Johnson's work focused on this principle, and he managed to utilize it in some of his designs. What he was actually tapping into is called the exchange force pulse. This is a magnetic field of greater value and strength than the magnetic field it emanates from. Feynman discusses the exchange force pulse in 3 of his volumes of physics. The exchange force pulse is achieved by flipping the spin of a magnet at just the right moment using exact configurations of magnets and magnetic materials. This gives you a momentary pulse of energy, nearly 400 to 500 times the strength of the normal field of the magnet. So to explain the exchange force pulse, I should first explain some basics, and then I will explain what spin accelerators are. Let's dial it back to the very basic to start with though. This is a standard magnet. Most of the textbook diagrams of a magnetic field that emanates from it look something like this. However, Howard Johnson discovered a sophisticated way to map magnetic fields and discovered that the actual field looks more like this. The fields of the magnet are actually electron spins. These spins are usually more dominant on one side of the magnet than they are on the other. In between these spins is what's known as the Bloch wall. This is the neutral center of the magnet where the magnetic field is 0. John Bedini refers to it as the delta 0. Howard Johnson designed magnetic assemblies that effectively moved the Bloch wall of the magnet. For example, by capping the north side of the magnet with a neodymium magnet, it moves the Bloch wall, weakening the south pole of the magnet while strengthening the north. Johnson was a master of crafting complex magnetic assemblies that moved magnetic fields around in precise placements and strengths. He could cancel out one magnetic field, strengthen another, modulate a magnetic wave pattern with ease. His assemblies are unique and bear little resemblance to anyone else's work relating to magnetic motors. And here's where things get really interesting. Howard Johnson knew how to momentarily flip the spin of a magnet, effectively making a north a south and a south a north. The way that he did this was by combining magnets on an armature composed of different magnetic materials into configurations that would trigger an exchange force pulse when another magnet came within close proximity of this armature. Most of his tracks were composed of neodymium, ceramic, and rubber magnets. Sometimes his cart magnets were Alnico magnets tipped with neos, and sometimes he used ferrite instead of ceramic. Discovering his exact configurations of magnets, their size, shape, and orientations, is the key to understanding how he accomplished his spin-flipping methods. Spin accelerators were used in most, if not all, of Howard Johnson's spin-flipping devices. Spin accelerators are magnetic assemblies used for crowding the magnetic fields at predetermined positions of a magnetic track. If built correctly, each spin accelerator will fire an exchange force pulse directly at the cart or rotor, accelerating it with each burst as the cart or rotor crosses a succession of them. By attracting a magnetic cart or rotor to a stator magnet and then flipping the spin at the Bloch wall of the stator magnet, you can expel the magnetic cart or rotor at an accelerated rate, eliminating your back MMF. So this is not perpetual motion. There are several possible ways you can do this. Howard Johnson employed various methodologies for spin flipping over the years. Most utilize similar magnetic materials, but oriented in different patterns. The idea was for the arrangements of magnets in the stator assembly to trigger an exchange force pulse as an armature magnet passed by. To build a system like this on an assembly line would require high-quality, precision-tested magnets. Standard magnets vary too much in field strength and have a great deal of defects in the magnetization process. Thus, they won't work well in an exchange force pulse assembly. It would also require precision cutting and shaping of the magnets and exacting detailed assemblies that would require specialized manufacturing processes to put them together properly. So how do you properly test an exchange force pulse system to know if it's operating correctly? There are several methods. You could field test the track in a lab and determine the magnetic flux density of the fields along the track in Gauss units. If the Gauss reading shows a steady increase in strength along the track, then that's proof positive that your assembly works. You could build 2 tracks and see if the first track accelerates the cart enough to break through the repulsion at the entrance to the next track. If the cart passes successfully between the 2 tracks without any decrease in speed, then that's a good indication that your assembly works. You could use a high-speed camera to determine if your cart is accelerating as it moves through the track. If the cart is receiving a steady flow of exchange force pulses, it should be increasing in speed as it journeys down the track. The most simple method is to restart the cart at various locations in your track and to see if it still accelerates completely out of your track without being pulled back in. If this works through several spin accelerator assemblies, double the size of your track. If it continues to work without any noticeable deceleration, then it's time to arc the geometry of your magnetic assembly and build a rotary version. There are so few people on YouTube that are experimenting with Howard Johnson's spin accelerator assemblies besides myself that I thought I would share a couple of short clips by YouTube user Flux Raptor. He does some really nice clean builds, very nicely constructed. And notice that he checks his flat track assemblies by restarting his cart in different locations on his track to show that it still works and is not simply exhibiting what I refer to as the spring effect before attempting to build a rotary assembly. Very few people experimenting with these types of assemblies know to do that. So my hat is off to him, and I recommend his channel. Fully understanding Johnson's work requires more than a basic understanding of physics. I can't speak for you, but I'm definitely not there yet. But the key to getting there is to learn something new every day and put what you learn into practice. Always keep moving forward. Thanks for watching. Join me next time when I will cover the third and final type of permanent magnet motor force system, the induction expulsion system. Do great things. The information that I'm about to share with you I've never seen anywhere else. I'm sure there are other people out there aware of this information, but I've never seen it shared before. It comes from years of studying, experimenting with, and building permanent magnet motive force systems. In case you missed it, in part 1 of the series I covered the Imbalanced system. I explained how it worked and how to test an assembly. In part 2 I explained the exchange force pulse system. I covered spin accelerators, spin flipping, and methodologies for how to test this type of assembly as well. I also pointed out that Howard Johnson is the only person I'm aware of that holds patents in all 3 systems. If you missed either of them, go check them out. The 3 types of magnetic motor systems are the Imbalanced system, which is the most common, the induction expulsion system, and the exchange force pulse system. Each of these systems can be built in linear or rotary motor assemblies. In this video I will be focusing on the induction expulsion system. An induction expulsion system, defined in simple terms, is any permanent magnet assembly that draws an object into its magnetic field and expels it. The object could be composed of metal or magnets. The The best induction expulsion system will do this with zero repulsion at the entrance of the magnetic assembly and zero attraction at the exit of the assembly. If an assembly has low-level repulsion at the entrance and low-level attraction at the exit point, it's still possible to use it for rotary motion or cyclical movement through a series of tracks, though it can be more difficult. It's also necessary for the start point and exit point of the cart or object to be on a level plane to be a true induction expulsion system. This must be done with nearly zero influence outside of the magnetic assembly used in a track or stator, though gravity can be used in conjunction with a magnetic assembly. However, the use of electromagnetics, such as magnetic wires collecting a charge from the permanent magnet portion of the device to redistribute into said device, would constitute an entirely different magnetic motor type. Thus, it would not fit into the classification set forth for the three types of permanent magnet motive force systems. There are a broad range of assembly types that could be classified as this type of motive force system. Permanent magnetic propulsion systems, also known as SMOTs, for example. Most of the ones that are commonly demonstrated on YouTube could not be considered true induction expulsion systems, however. I refer to them as simple magnetic toys if they aren't able to draw a steel ball into an assembly on a level plane and expel the ball on that same level plane. The amount of work that is required to align an assembly like this to properly function for cyclical movement is far more difficult than the simple design might indicate. Some great researchers on YouTube spent months and even years attempting this. A couple of the best are Michael Shaw. His channel is called The Batman. He's a good researcher and has some really great builds. There are some nice builds on YouTube user Wood, Brass, and Glass's channel. Another is Bill Mayhes. There are a couple of people, Greg Watson and Epidaxy, who claim to have built a running looped version of this system. This was pointed out to me by Stefan over at overunity.com. He has some information about it on his website. This type of assembly can be used to move a steel ball through 3 successions of gates, but requires some effort to ensure the system is level and that you're actually accomplishing any motive gain. Then there's this Howard Johnson gate, which he patented. By altering the electron spins of magnets in his gate, it will effectively draw a cart into the gate and expel it out the other side. For anyone who's ever built one of these types of assemblies, the first thing you notice is that there's a strong field of repulsion that you have to pass through before you get to the area of attraction at the entrance of the gate. So it would take some creative work to alter the assembly in a way that would cancel out most or all of that repulsion in order to build a rotary version of this design. Johnson worked on a variation of this assembly for one of his rotary designs. It was one of his most tested assemblies. You'll also notice that there are quite a few people working with other variations of this design, commonly referred to as a Bedini gate assembly. It passes a rotor magnet through a few gates and then comes to a stop. A properly functioning version of this type of device more clearly demonstrates over-unity than any other magnetic motive force system, which is one of the reasons why it's my favorite of the three types of permanent magnet motive force systems. One of the other reasons is the fact that you can also include one or both of the other two types of magnetic motive force systems into this type of system, or neither. So this can be a very complex assembly, or a very simplistic one, so long as it obeys the three basic principles. One, it has to draw an object, cart, or rotor into an assembly that is set up on a level plane without any repulsion at the entry point of the assembly. 2. Accelerate that object, cart, or rotor all the way through the assembly. 3. It has to expel it out the other side with enough motive force that it is prevented from being drawn back into the assembly. When you can successfully accomplish all three of these principles, you have an assembly that can be used to build a rotary or cyclical magnetic motor. So it's simple to test this type of assembly. Simply make sure that an assembly obeys all three of these basic principles, and then loop the design or arc the geometry. This completes my three-part series on the three types of permanent magnet motive force systems. Thanks for watching, and do great things.